Hello and welcome to Lesson 11 in Unit 2B, Quadratic Functions, Forms, and Transformations in our Grade 11 University College Math class. This is how to find the equation of a quadratic function given a graph or a data set. So we're going to look at two sort of discrete situations here. The first is if I give you a graph of a parabola, how can you figure out what the equation is? Similarly, what happens if you're given a data set? Is there any way to figure out what the equation is there? So we've got two different things to look at here. Let's just jump right in. So the first example is how to find the equation given a graph. So the steps are listed right here, but let me just talk you through it in a more, I guess, casual way. So when we're building the equation from a graph, and we can clearly see the graph here, the thing I want you to notice is that the easiest form for us to build a quadratic in is vertex form, which is right here. Y equals a bracket x minus h all squared plus k. That's the easiest one. So the first thing you're going to want to do when you are given a set of data, a graph, is to locate our vertex. And our vertex is located right here. So the vertex is at, and it's quite blurry, and I apologize for that. Our vertex is at 3, 8. So the h value is 3, the k value is going to be 8. So that's the first thing. The second thing we're going to do is find any other point on the graph that's not a guess. And what I mean by that is something that goes through an integer. So like a whole number rather than like, well, it's kind of sort of close. Maybe that's a half, maybe it's a third, who knows. So pick one that goes through an actual concrete point. Let's pick, actually, well, any of them will really work, but let's pick this one right here. They say the neighbor right here. So this is going to be 1, 2, 3, 4, and 6. So the point that we're going to be using is 4, 6. Any point will work, really, or any point after the parabola. Any point after the vertex. There we go. So what do we do now? Well, we have 4 variables spoken for. We have h and k and x and y. The only one that's missing for us is our a value. A is the only one that at this point is an unknown. A is not known. So what we can do is substitute all of these values into the vertex form of our quadratic and then solve for a plus k. So now we're just going to start replacing things. So if we're going to replace the vertex is going to be the h value is 3 and the k value is 8. We picked another point, that's our x and our y, so our y is 6 and our x is 4. So at this point, a is the only variable remaining we haven't spoken for, so we can figure it out. So let's start by following BEDMAS. There's our 6, our a, and we have 4 minus 3, that's 1 squared plus 8. Let's keep working through this, so that is now going to be 6. That's just going to be a, or 1a, I guess, plus 8. Let's bring this over to the other side by subtracting 8 from both sides. Subtract 8 from both sides, and that gives us negative 2 is equal to a. So at this point now we substitute our a value back into the like the raw form, or I guess the basic form of this quadratic and vertex form. So there's our a value, x minus, and our h value is 3, all squared plus 8. So the only piece that was missing for us was the a value. We took another point, substituted it into the equation along with the vertex, determined what a was, and then substituted it in 4a to get the actual equation. So that's one way you can do it. As I've said, I think a couple times already, any point will work. So let's pick a second point and just verify that that is the case. So the second point that I've indicated down here, this is just for kicks, of course. A second point, we're going to use 0.10. So that's this guy right here. 0.10. Now let's go through this same operation again. We have h and k, and now we're going to substitute in for x and y. Instead of 4 and 6, we're going to substitute 1 and 0. So 1 goes in for the x, 0 goes in for the y, and as we recall, the h and k values were 3 and 8. So there you go. Let's figure it out. So again, a is the only variable we have there. Inside the bracket, we have 1 minus 3, so that's minus 2, all squared, plus 8. There we go. negative 2 squared gives us 4, a's plus 8. We bring 8 over to the other side by subtracting 8 from both sides, and that's going to give us negative 8 equals 4a. And to isolate a, we divide both sides by 4, and we end up once again with negative 2 as our a value. So this just goes to show that you get the same result from any point on the graph of the function. So there you go. That's the first example. If you're given a graph, how do you figure out the equation? You can find the a value algebraically by getting the vertex and any other point, substituting it into the basic form of the vertex form quadratic, and then isolating a to figure out what the a value is. Another way to do it, and we're not going to really spend a lot of time talking about it, is probably what I'd call like the hack and slash, which is knowing that if this is our vertex, and from the vertex we go out 1 and down 2, and out 2 and down 8, then we know that this is going to be a vertical expansion by a factor of 2, in that 1, 4, and 9 have been amplified to be double what they would normally be. And of course the fact that it opens down means that these of course will be negative 2's. That's a hack and slash way. Nothing wrong with it. It's just it's maybe not as versatile if the plot pattern isn't obvious from the graph and your a value is going to be something ridiculous. Then knowing how to do it algebraically is also super important. So I'm going to stop this video here, and then in our next video we are going to tackle how do we determine an equation from a data set rather than a provided graph. So we'll see you in part 2.